Hey everyone, Michael Felizardo here, and today we're going to look at FRQ question 5 of the 2004 AP Calculus BC exam. Please keep in mind that this is on the no calculator portion of the FRQ, so a graphing calculator may not be used to answer this question. Let's get into it. So, a population is modeled by a function p that satisfies the logistic differential equation dp dt is equal to p over 5 times the quantity of 1 minus p over 12. Part A asks that if p of 0 equals 3, what is the limit of p of t as t approaches infinity? And if p of 0 equals 20, what is the limit of p of t as t approaches infinity? Now, to answer this question requires a basic understanding of the logistic differential equations. And for that, I will briefly review with you what those are right about now. Okay, so in order to understand what logistic differential equations are, I think it's important to understand the contrast between exponential growth and logistic growth. Now, if you've taken biology before, you may have already recognized these terms. We're going to talk about them today in terms of more of calculus and mathematics. So, briefly, exponential growth is the idea that a population, well, it's kind of obvious, grows exponentially. As in, as more time passes, the population increases at a more increasing rate over time. And this has no limits, so it'll just keep increasing forever and forever and ever and ever. So in order to account for this finite number of resources, we have this concept of logistic growth, which looks something like this. And so that kind of differs in that how this population levels off at this point, at this line, I would say. And this line represents the environment's carrying capacity. And so a carrying capacity is like the largest number that an environment can hold for a certain population. And once a population goes over the carrying capacity, it's likely to go down. So the basic logistic differential equation goes in the form of this. So the change in population over the change in time is equal to some sort of constant times the population times a quantity of 1 minus the population over L. L in this case is the carrying capacity. And so this part kind of resembles the exponential growth, but in order to account for the finite number of resources of an environment, we add this and thus turning it into a logistic growth. And so, going back to the actual question, you could see that this form resembles what we have here. In this question, we have dp dt is equal to r in this case is 1/5 times the population times the quantity of 1 minus p over 12. So we know that L in this case is equal to 12. So our carrying capacity is equal to 12. And what does this mean? Well, the carrying capacity essentially functions as a horizontal asymptote. A horizontal asymptote. And so let's say you have your logistic graph when you start at 3 and you have 12 right here. Right? Because we're trying to find if p of 0 equals 3, so if our initial population starts at 3, what is the limit of p of t as t approaches infinity? This is t, and this is p. So based on the graph we saw before, it's going to increase, and it's going to start decreasing once it gets near this carrying capacity. And the graph is just going to continue to essentially flatten out at this carrying capacity. So we have the limit, well, when p of 0 equals 3, the limit of p of t as t approaches infinity is equal to 12. And strangely enough, for the second part, when it asks that the initial population is at 20, which is obviously above the carrying capacity, you may ask, how will that work? Well, it's going to function pretty much the exact same thing. It's going to narrow, it's going to decrease in order to approach that carrying capacity. And it's going to keep increasing and flattening out at that carrying capacity all the way up to infinity. So when p of 0 equals 20, the limit of p of t as t approaches infinity is also equal to 12. Right? So that is pretty much part A. Now looking at part B. Part B asks, if p of 0 equals 3, for what value of p is a population growing the fastest? So we want to know when the rate is at its maximum. So when is the rate at its maximum? So how can we do that? Well, we could take the derivative of the differential equation. So we could take the derivative of p over 5 times the quantity of 1 minus p over 12. And that gives us, well, I'm just going to distribute this real quick. What is this? 1. This becomes p over 5 minus p squared over 60. So this just becomes 1/5 minus p over 30. And if you know, in order to find the critical values, just set this equal to 0. You set the derivative equal to 0. So 1/5 minus p of 30 is equal to 0. That's not 0. Okay. So p over 30 is equal to 1/5. Cross multiply. 5p is equal to 30. And p is equal to 6. So our population is growing the fastest at when p is equal to 6. And this isn't really necessary for answering the question, but it could really help later. If you notice, the population grows the fastest when it's at half the carrying capacity, right? Because 6 is half of 12. And I can quickly prove this when if you take the general equation of a logistic growth equation, which I previously wrote as R times P times the quantity of 1 minus P over L. R and L are constants. If you take the derivative of this, you get, and keep in mind we're not taking derivative into account of time, we're actually taking the derivative with respect to P. So we're just doing ddP of Rp times the quantity of 1 minus P over L. And that is equal to, just going to distribute it again because it helps. This is equal to R minus, why is it, yeah, okay, minus 2 RP over L. And we're going to do the same thing before, set it equal to 0. And so we have 2RP over L is equal to R. Cancel out the R's. And so we get 2p over L is equal to 1. We could multiply both sides by L and divide by 2, and you get P is equal to L over 2. And so this proves that the rate grows the fastest when it is half of the carrying capacity. And then we can verify it is a maximum, of course. It is not a minimum. We could quickly prove this again by making the table. So if you plug in L over 2, if you plug in any value less than L over 2, you should get a positive number. And if you plug in a value that's greater than L over 2, you should get a negative number, indicating a maximum. And so this maximum shows the fastest growth. So the answer for B is 6. If you look at the scoring rubric, you basically get 3 points for identifying all the answers, and that's essentially it.